So let's say that I give you a task. You're a developer, I'm giving you a task where you have to design a data structure that allows you to look up a value by its key. So, for example, let's say the key is a person's name and the value is an email. So you want to be able to look up a person's email if I give you their name. So you have to design a data structure that does this. My first thought is to do something like this, where you've got an array of objects, and each object has the person's name and their email. And so in order to look up someone's email by their name, you would just iterate through the array and see if the name matches the key that you're given. So if I want to look up, let's say, Chad's email, I would iterate through the array, and I'd be looking at this object, and I'd check to see if name equals Chad. It does not, so I'd continue to iterate. I'd see if this object's name equals Chad. It does not, so I'd continue to iterate, and I'd see if this object's name is equal to Chad, and it does, so I would output his email. And, in most cases, this works really well. I would argue that this is a great solution for most cases, because it's intuitive and it's straightforward, and these are very important qualities. If another developer comes on the project and wants to understand how your data structure works, this is important. And there's more to say about that, about how the structure is just an interface and they don't need to think about the internals, but anyway, forget that aside, it's a good solution. But what if we had a lot of people? What if there were I don't know, let's say this was Facebook and they have I think 1 billion or 2 billion users or something like that right now, and you wanted to look someone's email up. That would be very time consuming to iterate through a 2 billion element array. That would, that's very time consuming. So you might think, what about using a binary search tree? If you've heard of that, you'll know that that lets you look up things in O of log n time, which is a lot faster than O of n, which is what this would be. And yeah, that's true, we could use that, but could we do better? Could we get O of 1 runtime? Could we do this in constant runtime, where you look up someone's email given their name in constant time? At first glance, that seems I don't know, almost impossible, but in fact, it is possible. So let's think about how we could do this. So let's try to get constant time. How do we get constant time, just in general? Computer science, how do you do anything in constant time? And as far as I know, you need an array. Yeah, I'm pretty sure I can't think of any other way to do that. And the way it works with an array is if you know these 3 things, you can find something. So if you know the starting position of the array, how many bytes does each slot in the array take up, and the index you're looking for, you can find what you're looking for. So, if we are looking for element in index 3, what we would do is we know the starting position is 200. We know that each slot in the array takes up 4 bytes, and we know we're looking for index 3. So we would do this calculation and get 212, and that in fact is the starting position of index 3 in this array. Or my math might be off there. 0, 1, 2, 3. Nope, that was right. Okay. And more generally, to get index x, you do this calculation. The starting position plus the amount of bytes in a slot times the index you're looking for. So with that said, this might be really useful to solve our problem where we're trying to get someone's email from their name in constant time. If we use an array to store everything, we'll have 1 and 2. We'll have the starting position and the amount of bytes, but the only thing left is to solve for x. So we're going to have to be able to take the key, the person's name, and get the index from that. And if we can do that, then we'll have x, and we'll be able to look up the position. So yeah, if we have this magic mapping function thingy that can take a name and output an index, we'll be good. And maybe, I don't know, this function can just say, let's just look at the first letter, and if it's A, return 0, if it's B, return 1, C2, D3, etc. So if we had, let's say, Adam, Bob, and Chad, Adam would go in the first slot, Bob would go in the second, well, the 0 with the first, and Chad would go in the second index, using this function. And that would be great. Except that this algorithm here isn't really perfect, because what happens if there's Adam and Alex? Well, Adam, this algorithm, would look at the first letter, see that it's A, and it would return 0. It would look at Alex, see the first letter, it's also A, and it would return 0. So, then A of 0 is what? Like, you can't fit Adam and Alex in here, so there's going to be a collision, and that's not going to work. So, yeah, that's disappointing. This approach seemed promising, but maybe we could alter it, because it has taken us pretty far. So maybe we could solve this problem. And yeah, so maybe we could just accept there are gonna be collisions and try to work with that. So if we're gonna take that approach, let's think about how we could create this magic mapping thingy. Well, I'm sorry. let's just think about the question of how can we create this magic mapping thingy, this thing that maps a key to an index, without collisions. Let's think about whether or not that's possible. And let's say that our keys are words in the English language. We're restricting the domain of keys to be that. Well, the longest word in the English language is 45 letters. I could go look it up. English language is this guy right here. Pneumono ultra microscopic silicovolcanocoiosis. That's the longest word. Anyway, that was fun to try. So we could map every possible combination of 45 letters to a unique number. And in that case, every possible key would have its own value, and there wouldn't be any collisions, and that would solve our problem. But there are 26 to the 45th power. That's the number of possible combinations of 45 letters there are. And that's one of those numbers that is bigger than the estimated number of subatomic particles in the universe. So, like, we don't even have the computing power to store this, even in theory. Like, yeah, in theory, we don't even have the computing power. Maybe with quantum computing or something, but it's unreasonable to have an array that's so big. So, yeah, I think what we're going to have to do is accept that there are going to be collisions, and let's see if we can work with that. So, yeah, let's say that these are our possible keys. We're going to have to use some reasonably sized array that's smaller than this, and accept that there are collisions. And a little interesting note is that they call this the pigeonhole principle in math, where if you have 10 pigeons that you're trying to fit into n slots, that's impossible to do. There are going to be collisions, and you can see here that there are 2 pigeons that are being stuffed into this top left slot. So, with that said, let's think about the questions of, 1, how do we handle collisions? Given that they're going to occur via the pigeonhole principle, how do we handle them? And 2, how do we reduce the likelihood of a collision happening? So those are important questions to think about. But before going on to them, I just want to define this term here called load factor, which is the ratio of possible keys to the size of the array, the amount of slots in that array. So a load factor greater than 1 is where the amount of keys is greater than the amount of slots in the array, and that's going to be mean that there are going to be collisions. Like the larger the load factor, the greater the likelihood of a collision happening. And if the load factor is lower than 1, that's going to mean that there are more slots in the array than there are possible keys. So that's good in the sense that it reduces the likelihood of a collision happening, but it's bad in the sense that you're going to waste memory that way. Well, waste might be a strong word, but there is going to be memory that is unused in that situation. And to continue this aside a little bit, usually what they say is a load factor of about 0.8 is good. It's a good balance between these two things, where yeah, your array is a little bigger than the amount of possible keys, but you're not wasting too much memory, and these days memory is getting cheaper anyway, but you're not wasting too much memory, and you're reducing the likelihood of a collision. But anyway, yeah, that's the trade-off you have to think about with this load factor. But anyway, let's think about this question of how do we handle collisions? There are two approaches. One is chaining, and two is linear probing. But let's start off with chaining. So in chaining, instead of putting your stuff in the actual slot, the array slot, you're going to put a reference to a linked list. So this is going to point to a linked list. And your linked list is what's going to have your actual data. So let's trace something here. Let's trace this stuff. What happens when we insert, when we start off blank and then we insert Adam with the corresponding email? The first thing that's going to happen, let's say that we're using a hash function that looks at the first letter and returns the index. So it's going to see that the first letter is A, and it's going to return an index of 0. And then it's going to see that nothing's in this slot yet. So because there's nothing in the slot, we're going to create a new linked list that's initialized with a node, this Adam node here. And really, it's going to be an object key value pair that's going to look like this. I'll write it out. 1 second. It's going to have key of Adam and a value of Adam at gmail.com. So this object here is what's going to be in the node, in the linked list. I just did this because it's more concise and it can fit. Okay, so with that said, let's continue to trace. Let's see what happens when we insert Alex after we inserted Adam. So it's gonna look at this key. The hash function is gonna look at this key, and our hash function is looking at the first character, and it's gonna return, because the first character is A, it's gonna return 0. But we got a little situation here because index 0 already has a linked list. So what are we gonna do? Well, what we're gonna do is we're just gonna push a new node onto that linked list with this data here. And this is how the chaining approach to collisions works, where you're storing a linked list in each slot. And if, a linked list, they can grow. So you just append something onto the end of it if there's, something in this slot already. And that's what happens here. And just to continue a little bit, if we try to insert Dave here after inserting Adam and Alex, this is going to map to index 4, and because index 4 was empty, it's just going to create a new linked list here with a node of Dave. Okay, and let's think about how the find operation works here. Well, it's going to look at the key, and it's going to look at the first character in the key. It's going to run it through the hash function, which is going to output 0. And since we're chaining, we can't actually just look and return the contents of this slot, because that's just a reference to the linked list. So then we're going to have to iterate through the linked list, looking for a key of Atom. So we're going to start here, see if this, it's going to look like this. It's going to, like, if node.data.key equals Atom. It's going to run a check that looks like that. And if it does, return, otherwise continue to traverse. Okay, and in this case, the first time it does, so it's just going to return node.data.value, which is the email. Okay, and let's see about Alex. Well, Alex is it's gonna be this index, and then we're gonna traverse the linked list until we find Alex, and then return it. Similar for Dave, pretty straightforward. And some notes on this approach, the chaining approach. You might have noticed a bit of a contradiction here. So we're looking for something that's O of 1, a constant time find operation and insert and delete. But we've got O of n to traverse the linked list here. And like in the worst possible case, what if our names were like Adam, Alex, Andrew, Anthony, Amanda, Andy, Allie, all A's? We would end up basically just having this array that's empty except for this index points to this big linked list. So it's essentially just one big linked list. And to find anything, it would be O of n because you have to traverse this long linked list. And we're looking for something that's O of 1. So you might be thinking that this is a bad approach, that this isn't solving our situation. And you'd be right that it's not perfect. It's not going to guarantee O of 1 in every situation. And I'm being a little loose with my wording here. But basically, yeah, that's the cost, is that there's going to be some collisions, and in the case of a collision, it's going to be O of n to find it, where n is the size of the linked list. But the goal here is that we use a good hashing function so there aren't a lot of collisions, and we use a good sized array with a good load factor that'll also reduce the likelihood of collisions. And yeah, the goal, like if there are a lot of collisions, then the hash function is bad. But we can write a hash function that makes it unlikely that there's a collision. So in most cases, it's going to be O of 1. And again, I'm being loose with the words here. Yeah, on average, it's O of 1. A second thing you might have thought is, well, okay, so we're going to, because there are going to be collisions, we have to point to some other data structure that has all of the things that hash to this slot. So here we're pointing in this 0th slot because there's multiple things, Adam and Alex, that hash to that slot. We have to have some data structure here that contains Adam and Alex, and that we can traverse to find either Adam or Alex. So why not use a binary search tree? Because a binary search tree, you can find things in O of log n time, which is a lot faster than O of n, which is what we have with the linked list. So yeah, you might have had that thought, but the response to that thought is that so big O is talking about worst case. It's a worst case situation where we're looking at how long something takes in the worst possible case. And the thing is that that's not the only thing that matters. A binary search tree, actually, for small n, it's actually more expensive to use. It's slower to use than a linked list for some reasons, whatever. But yeah, for small n's, like less than, I don't know, 10 or 100 or whatever, it's slower than a linked list. And even though for a large n it's going to be faster, it's going to be log n, for small n it's going to be slower. And the idea here is that we're using a good hash function, and n, which is the number of things in a slot, is going to be small. So in most situations, a linked list is actually going to be faster than a binary search tree. And I'm going to link to a good article on Wikipedia. Well, a good section of an article in Wikipedia that discusses this. And yeah, the article also talks about how there are situations where you'd want to use a binary search tree instead of a linked list. It completely depends on your application. And you might have some application where you like really need to guarantee that it's never going to be, more than log n runtime to find something. And in that case, you might want to sacrifice a little average time to find to optimize for like the worst case. And in that case, you might want to use a binary search tree. So let's now talk about the second approach to handling collisions, and this approach is called linear probing. So the way linear probing works is, to explain it, let's run through a trace here. Let's say that we insert Adam, and A maps to index 0, and we put Adam in. That's all good. Then let's say that we insert Alex after having inserted Adam. Well, A maps to index 0, but index 0 is populated. So what are we going to do? Well, with the linear probing approach, we just put Alex in the next available slot after Adam. And like, I don't know, let's say this was like Chad and Corey, and Chad was here and we're inserting Corey. Corey would go here. It wouldn't go here. Corey would go after the index that the hash function outputted. But anyway, linear probing, we put it in the next available slot after the index. And you can see that this is problematic because this slot is where things that start with B are supposed to go. So now if we try to insert Bob, now Bob can't fit where it's supposed to be, and it has to take up this slot. And you can see that this approach, linear probing, it increases the likelihood of collisions happening. But the advantage to it is that it saves memory. With the chaining approach, we're creating this additional data structure that takes up memory. But with the linear probing, everything in theory fits in this array. So that's an advantage to it. And the disadvantage is obvious. It increases the likelihood of future collisions. And let's talk about the find operation. So if we are finding Bob, what we're going to do is first we're going to look in the correct index and see if Bob is there. And if it is, then great, we'll return it. But if it isn't, then we're going to have to traverse this array until we find Bob. So similar to a linked list, that's going to be O of n, where, yeah, we have to traverse the array. And something else to add about the linear probing approach. So what I described is where you just go to the next index, but there's a bit of math involved where you can go to, like, I don't know, you can skip 2 indexes or 3 indexes, or like a varying amount, like 2, then 4, then 8, or something like that. And I'm not going to go into this, but people study this and figure out like the fastest way to do stuff. And yeah, you can read about it if you want. It's beyond the scope of this video. Okay. So now, so there were 2 questions. Where did I write those down? So back here we had 2 questions. One is, how do we handle collisions when they occur? And 2, this is the second question of, how do we reduce the likelihood of a collision happening? So let's talk about that second question. The answer to that is to use a good hash function. And before I get into this, I want to say that like this is beyond the scope of this video. There's a lot of math and stuff involved in using a good hash function, but I'm just going to give a very brief survey of it. So there's sort of two parts. You start with your key, and it's going to end up mapping to an index in the array, but it's done in two parts. First, you get a hash code, and then you use a compression function that compresses the hash code into this finite set here. Yeah. And yeah, so like I said, it's a big topic. It's more of an art than a science. But one little hint, one little example of a good practice is that you want to use everything in the key. You want to use everything, because if you, let's say, only use the first 5 characters, then Andrew and Andre, their first 5 characters are the same, so they would hash to the same index, and there'd be a collision. So to minimize the likelihood of a collision, you should use everything in the key. Okay, so yeah, like I said, it's a big topic. You can go read more about it if you're interested. The last thing I want to talk about is resizing. So first, recall that the load factor is the number of possible keys over the array size. So if we have 3,000 possible keys, an array size of 2,000, 3,000 possible keys and an array size of 2,000, the load factor would be 1.5. And if the load factor is too large, there's going to be a lot of collisions. Like you can imagine, if this was huge, there'd be a lot of collisions, because it's trying to fit, think about the pigeonhole principle, a lot into a little. And the small load factor is, we'd be wasting memory. So if you want to think about the pigeons, you can think about, let's say there's like 100 slots and only 5 pigeons. So they can't, there's going to be empty slots. And like I was saying before, around 0.8 is typically pretty good. But anyway, as the load factor changes, and as we like run out of room in our array, we might want to do some resizing to keep things efficient. So you can have the hash after you insert and remove, you can check the load factor, check how many slots are open, and you can have it grow or shrink. And again, this is also, there's a lot of math involved in how to do this efficiently, which is beyond the scope of the video. But I just wanted to note that this is something you can do to make it more efficient. And finally, just one thing to note is that you can't just copy the things in your old array to your new one, because when you put things in the old array, you hashed it with the size of this old array. So the index that was outputted from the hash function was based on the size of this old array. But now that you have a new array, that's sort of invalid. You're going to have to rehash everything based on the size of the new array to get the correct index. Okay, so that's all I've got. As you can see, the hash table, it allowed us to solve our problem where we're trying to look up a value by its key in O of 1 runtime. And there's some qualifiers to that. It's really, on average, it's going to be O of 1. But I think this is a pretty cool and elegant data structure. And hopefully it make some intuitive sense to you.